Hello, good morning, and welcome to this almost last session of this wonderful symposium. Today we have two parts of the session. The first part with 3 presentations is about the LIGO-Virgo-CAGRA collaboration, a huge project on ground and their experiences regarding visibility outreach, and another future project, Cosmic Explorer. Then after the break, we will have 2 presentations from our friends and colleagues in China about the Tianqin and the Taiji project, and about future ideas to go in space with missions beyond Visa. The first presentation is by Livia Conti from INFN in Italy about LIGO-Virgo-CAGRA collaboration and some questions regarding presentations and visibility. Please go ahead.
Yes, okay, let me share the screen. Okay, yes. Okay, so hello everyone. So my name is Livia Conti. I am a researcher at INFN in Padova. And as I said, I am a member of the Virgo collaboration. And today I want to talk to you about the issue of visibility of Virgo, and more recently also of CAGRA in the scientific literature. In summary, the issue of the visibility of the LVK. And this is the list of people who have collaborated to this work. And we are all part of the LIGO-Virgo-CAGRA collaboration. So this is the outline of my talk. So I will start by explaining to you what we mean by the issue of the visibility and why we care for it. Then I will discuss our approach to solve this problem and at least how to mitigate it. And so I will present some results and conclude with future work. So let me start with some history, which many of you already might know. Anyway, in 2007, LIGO and Virgo, who are ground-based gravitational wave detectors, have agreed to join in a collaborative search for gravitational waves. And since then, they have operated as a sole machine, a single machine, and the major results have been developed and co-authored by both the collaborations. And this wide collaboration has been joined in 2020 by CAGRA, the ground-based Japanese detector for gravitational waves, and this realizes the worldwide network of gravitational waves. And this is what we call the LVK collaboration, LIGO-Virgo-CAGRA. And in principle, and in the intention of the scientists, this is a collaboration among peers. However, this is not always recognized in the wider scientific community and as well in the media. And an effect of this lack of recognition is that the collaborative work and the results that are achieved by the collaboration are not attributed correctly. So let us be more precise and state a little better what we mean by this problem of the issue of this problem of the visibility. So the problem we want to address is that the contribution of Virgo as a collaboration and as a detector is not fully recognized in the scientific literature. And what we observe is that when discussing gravitational wave discoveries and results, in the text of some papers, people refer systematically to LIGO, where instead LIGO-Virgo or LIGO-Virgo-CAGRA should appear. And I want to stress that this is not a problem of missing citations, but we are concerned with the narrative of the scientific developments. That is to say, on how science is told. In other words, our concern is not if Virgo papers are cited, and they are cited, but rather if Virgo is placed correctly and it is associated with its science in the text of the articles. And more recently, a very similar issue appears also concerning CAGRA when citing results from LVK collaboration papers. So here I make a couple of examples of what I'm talking about, and these are our starting points. So where we started from. The first paper is a paper by the Gravity Collaboration, which is an influential paper, and it has made some impact. And in this paper, we find sentences like the ones that I put here, in which they only mention LIGO, the LIGO black holes and the LIGO measurements. The second paper is a less known paper, but again, we have this issue with the events only attributed to LIGO. So it is clear that there is a problem. But why do we care for this? We care because we believe that this biased narrative can produce a detrimental effect, both in the short and the long term. And the scientific community should be able to associate Virgo and now also CAGRA to gravitational wave discoveries and science. And these bias impacts have several impacts. So in particular, impact affect badly the work of hundreds of people at work at LIGO, at Virgo and CAGRA, and in particular on the career of young scientists. And it also has a bad effect for defending agencies. And in the end, this is also reflected on how we are represented in the media, and hence has an impact also on the wider public. I want to point out that we have raised this issue in front of the Virgo Collaboration first about 1.5 years ago. Then in March this year, we've raised this to the LVK Collaboration. And in both cases, we have received large and positive feedback from our colleagues, meaning that this issue is felt as important by the whole LVK Collaboration. And now let's see how we tackle this problem. Our idea is to give feedback to the authors of papers that show a problem. So we send them an email where we explain the problem, and we show where their paper contains an issue. And we ask them to edit the paper and fix it. Our goal is not only to fix the specific issues in that specific papers, but rather to educate the authors. And by doing this, we aim to educate the scientific community by doing this in over an extended amount of time. And this is in more detail our workflow. So we have a script that automatically checks the papers that are posted every day on the archive. We focus on GRQC and AstroPH. This script produces a list of possibly problematic papers. Then these papers with the warnings are checked by volunteers, so people from our group, in bunches of 1 week. And then we send an email to the authors to ask the authors of really problematic papers to edit their text. And sometimes there is an email discussion with the authors to explain our viewpoint and our work. And this is it. Let's see some results. In 2011, we started this process, but not in a well-organized way. A more systematic approach has been taken since the start of this year, thanks also to the fact that we have more volunteers. And our aim is to cover all the weeks of the year, and we are already progressing well. So this is the results from the first 7 weeks of January, starting from mid of January. The scripts has processed 4,000 papers, and we have found 600 which cite LIGO, and among them 200 have some alerts, and these are those that we manually inspect, and among these we found 40 papers with major issues. So about 7% of the papers who cite LIGO show some really big issues with the visibility. And in average, we found 6 papers per week to have major issues. And the authors of all such problematic papers have been reached by our email. But we have not done this only for these 7 weeks, but we have, in this year, we have already analyzed papers from 27 weeks, so all weeks starting from mid of January. And manually, we have scrutinized 800 papers that have appeared on the archive. And we found 212 papers with serious issues. And so this paper we sent emails, and in average we found 8 problematic papers per week. Of course, these are the papers that have just appeared on the archive, so we are not assessing the real impact of the papers. So, of course, the papers who attract many readers and many citations, so influential papers, will contribute more to spread the same misconception. So, but we treat all the papers at the same level. Again, some results: about 17% of the authors which are contacted by us are reply. And I'll give you later some examples of their replies. And usually they understand the issue, and they express the willingness to edit the papers at the next occasion. However, we are not following up the papers to see if the changes that they promised are actually implemented. So this is something we don't check. This I want to give you, since there is a short time, I want to give you just a few examples of papers with issues, and I want to give you here to show a change in the paper that was achieved after our email. So in this paper, they showed a table with data from the first catalog of gravitational wave transients, and which was referred as LIGO only catalog. And then after our email, this was changed into LIGO Virgo correctly, recognizing the role of Virgo. And here are some more examples, but anyway. And here I want to give you some ideas or some examples of replies that we have received. So I will not read all of them, but just give you, I have highlighted in red the most important parts. So the first 2 replies indicate that people do not really know the real contribution of Virgo. So I thought that the original pre-2017 papers were just signed by LIGO. And also this expression. So this, they don't know the real contribution of Virgo. The replies from 3 to 5 show that people are aware, but somehow fail to fully recognize the role of Virgo. And the last 2 replies support our idea that doing this work, we do educate people and not just fix the scientific papers. So this is a hope for the future that we are in the right direction. Then to get some results, as I said already, we need to educate the community and not just a few people, so the few authors. So we estimate this process needs to be continued for at least about 1 year. So this time is we estimate enough to survey a good fraction of scientists which are active in our community, scientific community. As a future work, and this is my concluding slide. So I want to say that awareness on this issue is increasing and is already high within the LVK. The LVK after March, following in the past few months, have decided to put in action some more. To put in practice some more action to solve the problem. And among these additional actions, we want to inform the editors of major scientific journals so that they can check how the LVK is referred to when they proofread their articles. We want also to contact the managers of preprint repositories such as Inspire and Archive to change the way our papers appear when cited from their database, because this is sometimes also the way we are cited and makes an issue, so can bias the readers. And we want to identify, and we have identified a unique acronym for being cited, and we want to explain what the LVK collaboration is. Okay, and this was my talk, and thanks for your attention.
Thank you very much for this very important talk about this very serious issue. And thank you also for staying on time. That means we have now 4 minutes for questions and discussion. So please type in the chat or just raise hand and unmute yourself. Yes, please, Martin.
Yeah, thanks, Gerhard. Thanks, Lydia. Very nice talk. I have a kind of a comment and a question. The comment is partially wearing my chair of the advisory committee hat, because some people may be thinking, well, what's this got to do with LISA? And for me, the project you've been leading is potentially quite important in the sense that LISA is a joint ESA-NASA mission. And I think it demonstrates that you know, we need to be clear with other scientists and with the public on what that means. You know, we don't want, for example, the public to get the impression this is just NASA or indeed just ESA. And it's good to see that if you take proactive steps, then you can achieve some good results. So that's my comment, a long comment, sorry, but the question is rather shorter. And it's just to ask, how long do you think we will need to be proactive like this to really, you know, make a kind of permanent change in the scientific community, so that we no longer need to check so carefully, and because we can trust that they will always refer to LVK? Do you have a sense of that?
Well, no one knows, I think, but we as said, we think that we need to push this effort at least for 1 year. So the idea is that in 1 year, it's a time between one paper and the next one of the same author, let's say. Obviously, things changes, and we will need to check. And I cannot, I don't know the exact answer, but at least 1 year, I would say.
At least 1 year. Yeah, thank you.
Yeah, thanks for the comment with about LISA. Indeed, this was the reason for giving the talk to this audience.
Yes, that's very relevant indeed.
I don't know if you have already experienced or you are already experiencing this.
Well, more in outreach than with other scientists, but in outreach, I very frequently get, oh, that's a NASA mission, isn't it? And it's just because NASA is such a recognized global brand, you know, there's not really much we can do about it, but your project demonstrates that we can do something if we are proactive.
I was writing in the chat. Currently, LISA is an ESA mission with NASA participation. Yes, indeed.
Forgive me, Oliver, I was using a bit of shorthand, but you know what I mean. You know, that absolutely demonstrates that we need to be careful that the public don't think of this as a NASA mission. I will defer to others.
Martin, absolutely, I know what you mean. And I don't mind calling it an ESA-NASA mission, not at all. It's just because of exactly the problem that NASA has a much bigger pull in terms of PR and public recognition. We need to be, I'm hesitant to say careful, because the clear way forward there is not to trying to minimize the NASA pull on things. It is to maximize the ESA kind of outreach and being available or being visible to the world. It is a somewhat uphill battle, I can tell you, as probably everybody who worked with ESA outreach will have experienced. We simply don't have the resources that NASA has, but we've seen that in other missions, you know, where despite the fact that it's an ESA mission, it's usually considered a NASA mission. I mean, SOHO is a good example, and yeah, I think we have to fight that a bit.
Thank you. We have to move on. The next presentation from Hannah Middleton about what's called the LIGO magazine, maybe just in point. Please go on.
Hi, everyone. I'll just share my screen. Okay, hopefully that looks all right. Yes, so I'm going to talk about the LIGO magazine. This is a presentation also with Anna Green. So our plan is to have a run through this presentation and then have like a discussion afterwards. So I'll run through the slides and then Anna and I will answer any questions. And I also see there's Sasha obviously online, and I saw Suzanne and Paul too. So there's lots of editors who are available to answer questions. So the point of this talk is that the LISA community is recently, or the Outreach team has been starting to think about whether they'd like a LISA magazine. So we were here to sort of share our experiences of working on the LIGO magazine. Okay, so as an overview, this is, I'll say what it is and why bother having it, basically, why it's a valuable resource. And then a little bit of our experience of how the editorial team works, and then what you can read inside of a typical issue. So, so it's a twice yearly publication by the LIGO Scientific Collaboration. And I know what we were discussing just now with Livia. It's true that this is a LIGO is a LIGO publication, but we also include updates from Virgo and Kagra authors as well. It's free to download and read, so the website is here. And it is aimed at both the gravitational wave community and the public. So we're performing two tasks here. We want to educate ourselves about what is going on in the gravitational wave community. So as an example, I work on data analysis. I know very little about what's going on at the instrument and on the experimental side. So it's to educate ourselves. But we also want to inform the public of what's happening in gravitational wave science. And we've recently joined Twitter, so you can follow us as well. So what can you read about? So the LIGO magazine includes personal stories. So it's like the inside story of people working on the science, their personal perspectives and experiences. We have news and discoveries, and these are often reported by early career researchers. Advice for and by early career folks, and engagement activities from around the community, and more things. So this is by the community and for the community. And why bother? So why have this magazine? So we really want to emphasize these personal stories. Like, scientists are people are working on these massive discoveries, and it's the stories of people waking up in the middle of the night to go and check on gravitational wave alerts. This kind of what is it like being a scientist, basically. It also presents opportunities for early career researchers to present their take on the big results. So we have early career researchers talking about the catalogue papers, the big discoveries, the latest work at the sites on commissioning and the technology improvements. And we also want to share news from inside and outside of our collaboration. So the updates at the sites, as I say, but also from beyond. So from the LISA community and pulsar timing array communities, so the gravitational wave community as a whole. And also to highlight these outreach and public engagement activities. There's so much going on, and to highlight this, I think, is really valuable. So how is it used? Like, once you've got this resource, it's useful for us as a community. We can learn about each other, learn about the collaboration. And I won't read all of these, but it's used in many different forms. So obviously for outreach, people take them to outreach booths and give them out to to folks who are interested in gravitational waves who may not have, sort of as general public audience, and visitors to departments, our own students, and also government officials. So Dave writes here said he used to go up to Washington to meet with government officials and would give a magazine to these junior and senior staffers. And I also particularly like this one from Eduardo. So this is for our own perspective and current students. So I think that finding a community is important to students, and the magazine is pretty good at describing our world. And of course, we point the online version to as many places as we possibly can. So in social media, blogs, outreach events, talks, and any way you can advertise it. So I'll say a little bit now about how the editorial team works and sort of our experience of producing a magazine. So they're all volunteers from the LIGO community, and it's led by an editor-in-chief, which is me at the moment, and a deputy editor-in-chief, which is Anna. The team meets online a few times per issue, but the majority of the work is actually done via email and instant messenger. And we work closely with Sasha and Builder Science Communication for the layout. So this lecture, the layout is professionally done. This is what our website looks like too. So in terms of actually publishing an issue, we normally start about 5 months before the publication date. And this is sort of getting in touch with authors, deciding which topics to cover. And it's published during each LIGO Virgo Kagra meeting. So this is really a hard deadline. So it has to be there at the meeting. And so I guess if the LISA community is thinking of having a hard deadline like this, my advice would be to build in plenty of contingencies. And it can be a little bit of a balancing act, because sometimes articles have to be delayed because they're either too long to fit in the page count, or they're not ready in time, and we have to print on time. So some sort of general thoughts on building the editorial team. I think it's important to aim for a mix of perspectives and seniority. So try and represent your collaboration through the team, both in terms of having early career researchers, perhaps senior folks too, the topics that you cover. So what are these people working on? You don't want it just to be people working on the instrument, or just people working on the data or the astrophysics. You want a range, and different institutions as well. And I think this is a good aim for the team, but also a good aim for the article content as well. And it sort of grows naturally because you have people who know what's going on in different areas. It works very well when individual editors are proactive. So you need to sort of keep the ball rolling with authors and keep good communication back and forth with the team. And you also need people to take responsibility and follow up with folks to get the issue out on time. And this is basically just loads of emailing. Okay, so I'll go back to the magazine itself and just say a little bit more about how it's formatted. So it's 36 pages long. We have a high quality design for PDF and print. And we print, so it's obviously free to just read and download online from the LIGO website. And we do a limited print room of 500 copies. And these are distributed between the observatory sites, the meeting venues, and a few institutions. So we try to share them out as best we can. And the magazine is supported by the Max Planck Institute for Gravitational Wave Physics, AEI, and Caltech as well. So I'm almost at the end. So this is the typical issue sort of format. We have a few long articles, which is like, could be 4 pages or more. And these are like feature articles of the latest commissioning updates, or the latest upgrades to the detector, the latest results, the big discoveries. And in the most recent issue, this was we had several pages on the catalogue results coming out. And then we have several shorter articles, which can be all sorts of things, and several regular features. So normally we have a LISA update, some little quick read explainers, which are often illustrated by Natsini Kibunshu, a work after LIGO feature where we catch up with folks after they've who were previously members of the collaboration on like a wide variety of jobs that they're doing now. We have advice for and by early career researchers, and a news piece where people can anyone can submit a short career update or news story from themselves. So in the latest issue, this shows what we've covered. So many of these regular features. To the LISA update, our explainer was how did cryogenic detectors work? And we had a really nice article on class discrimination in academia. So we're trying to also cover these sort of socially important topics in science, as well as people's personal perspectives of working in gravitational waves. Okay, so this is the last slide I have. So in summary, I personally find, but this is a lot of fun. I think it is a lot of work, but we find it really enjoyable. And I would say most of all, the advice would be to have fun with it, be creative, and try and to make something that's fun to read, fun to produce. And just to advertise the September issue, we'll be celebrating 10 years of LIGO magazine in September, so watch out for that online. And yeah, that's all I have. And I think Anna and I, and I guess the other editors online, can also answer any questions that you might have.
Thank you. And please excuse me for forgetting to introduce Anna Green as second speaker of this. Yes, a question, please. Andrew, you had raised your hand, but that was maybe not a question. We have 8 minutes for discussion, and I think there's a lot of things to discuss.
Simon here. I can't raise my hand. I don't know why not, but I could speak.
Please.
Hi. Obvious question. How do we copy this for LISA? How do we get funding within the LISA project? How do we find the awesome people doing all the work?
So I think we can answer in terms of finding the people to do the work, but in terms of the funding, I think this is something that probably needs to be discussed internally for LISA. I guess for finding the people, you should look for people who are enthusiastic about it, and both in terms of the editorial team and the writers as well. And I mean, I think it's a case of like, if people are doing interesting stuff and people are having interesting experiences all the time, we just need to ask them to write their stories down. And people don't necessarily realize that what they're doing is like something that would be cool to read about in a magazine. They just think it's their day-to-day, but it's like those stories are really out there. So Anna, I think.
Yeah, I was thinking maybe we can say a bit about the size of the team you would be looking for as well, because that can maybe seem intimidating when you're starting from scratch. So I think obviously Hannah and I are kind of leading and trying to find editors and this kind of thing at the moment. But the core editor team would be, you know, maybe 3 or 4 very active people per issue, and then the editorial team would be maybe order 10, something like that. And then finding people to actually write the articles, that then comes from either you hear something that you want to know more about, and so you seek out someone that can tell you about it, or you know someone through the grapevine, that kind of thing. And so the levels of commitment that is needed by those team members vary quite drastically and can be quite flexible, and should be.
How good is the retention of the team? Are people dropping in and out constantly, or do you have like the core team that is on there for years and years?
Yeah, so there's a few different durations, I guess, that people would have. So you can look maybe the editor role. We're now on the 3rd editor. So those tend to be the longer serving things. And then we have some members of the editorial team that have been on since day one and still are, and have contributed more and less at different phases through that. And then we have some new editors that have just joined and they're having their first issue now. Maybe they will stay for 1 issue, maybe they'll stay for the next 10, who knows.
Cool.
Thank you. Stefano?
Yeah, thank you. Very interesting talk. Just maybe I missed it. Is this a full-time job for the two of you?
No.
And what fraction of your working time is?
But I think for me and Anna, it takes a good chunk of time. We're both postdocs, right? So we're doing it in our like besides our research.
Yeah, so the entire team is voluntary, but at least within LIGO, we're starting to be a little bit better about saying, okay, how are we contributing to the collaboration? And then this becomes part of our work as members of the collaboration, but we don't have a specific allocation or pay from this.
Yeah, I was following on the question from Simon, right? If we have to find dedicated people that do this as their only job, that would be difficult. But if you can do as say 20% of your time, that's different, right? Thank you.
Yeah, the workload also varies dramatically as you go through each magazine cycle. So I think right now, Hannah and I are reaching the busy phase, trying to pull all of the early drafts into final things that are printable. But there's some downtime just after each issue is released when you can just do your research.
Thank you.
More questions? There's a comment from Martin Henry. It's recognized as a key contribution to the LSC Memorandum of Understanding return. Maybe I have one question referring to the first talk of this session. Is there any discussion or prospect of making this an LVK magazine?
I mean, it has been thought about. So I think the tricky thing is that this is something that's been grown out of the LIGO collaboration. So if this was to be adapted into a LIGO Virgo or a LIGO Virgo Kagra magazine, I think is difficult. It should be a new thing, which is made sort of jointly between the collaborations rather than, yeah, I think if you try to change this magazine into LVK magazine, is at risk of it sort of looking like it's still the LIGO magazine because it wasn't born from all three collaborations. I don't know if Olivia also wants to say a little bit about that.
Yeah, I agree with you, and maybe within Virgo and Ego especially, we are considering the possibility of doing a magazine specific to Ego and Virgo.
Yeah. Sasha?
Hi all, thanks Hannah. That's a really nice talk. We in Upper Reach in LISA we discussed setting up a group to begin with and just discuss our options and see where we go, because we are approaching it from the other end actually as a LIGO magazine, where it really grew for a long time. We've got this kind of benchmark now and see if we aim for that or do something different. So I think it would just be nice to gather a small team of people who are interested in this kind of work and just discuss what we should be doing and see if we can come up with an idea which you could present to the consortium and find these authors, and so try to just take it step by step. And we've set up the group, and if you would like to take part in this, it's got an email already. It's lisamagazine@lisamission.org, strangely enough. So please just drop us a line there and see if we can get a kind of critical mass for a team. Thanks.
It's also in the chat. Yes.
Posted in the chat.
Good.
Thanks, Sasha. Just to add to that, I think I said it in the talk, but this is really fun it's a nice thing to work on. So you can really have fun with it. So
yes,
I
absolutely.
encourage people to do it.
And it might sound stressful, but in reality, we always manage to juggle these deadlines and we give ourselves plenty of time. And it's actually easy getting stories. We just approach people after interesting talks or read about some interesting results in a paper, and we just say, hey, don't you want to write maybe a page or 2 pages? And these kind of large feature articles, they're more or less determined by these consortium milestones anyway. So we had 03 now, it's going to be 04 commissioning and begin of 04 and so on. And it will be the same in LISA, I'm sure.
Yes, and sometimes we reuse texts also for other purposes, for media, for instance. We have one example from LISA currently, because we did the MFR press release, and Martin Gehler wrote a very good article for LISA. And I'm using this article also for journalists as a background information. So we can always use these texts and also the images for other things.
Yeah, also for web pages and such.
Yeah, yeah.
Okay, thank you. So we are perfectly on time for the next presentation, which is about one of the two future ground-based large projects. It is by Paul Fulda from Florida. Please.
Okay, just let me share slides here. Okay. So thank you for giving me the chance to talk about Cosmic Explorer, which is this concept for next generation ground-based gravitational wave observatory. So let me get right into it. I'm giving this presentation on behalf of the Cosmic Explorer Consortium. So I will talk about several aspects of this concept, a little bit about the actual observatory design, but a bit more about science case. And then since this is the LISA Consortium, the LISA Symposium, I'll try to talk about some of the overlaps that the science case for Cosmic Explorer has with LISA. Okay. So in the title, I call it a next generation ground-based gravitational wave detector. So just a little bit of background on what that really means. So you can kind of broadly separate the detectors and their various incarnations into the initial detector phase, where we had LIGO, Virgo, and GEO 600, for example, along with others. This generation of detectors demonstrated that the technology was feasible for precision laser interferometry on a kilometer scale, and they reached design sensitivity in most cases, but did not detect any gravitational waves. The next generation to come along was the advanced detector generation, like advanced LIGO and advanced Virgo. And these, obviously, as you all well know, have now been enormously successful in detecting 90 gravitational wave events to date, and then with many more to come, surely in 04 and 05. And so what I'm talking about here is the generation beyond, next generation. So that's in the US, the concept there is Cosmic Explorer. In Europe, it's Einstein Telescope, and then you may hear about others as well from different parts of the globe. So what does this next generation mean? What's the step forward here? This is slightly different in that we're really considering entirely new facilities now. So not upgrades to existing facilities like the advanced generation, but new facilities. And then in terms of the scope of the science that can be produced, we're talking about moving from sporadic detections to precision observations for detections we do make, and a cosmological survey of sources. So the kind of range we can achieve with detectors of this generation puts us well into the large redshift kind of regime, and we're really doing cosmological science at that point. And as I'll mention a bit more later, there's the timing hopefully works out so we can have contemporaneous observations in multiple bands of the GW spectrum, giving us some good synergy with LISA. So I like to think of this leap from the advanced generation to the next generation as really something like going from the first telescopes to the kind of extremely powerful telescopes that we use to do cosmological science today. Okay, so a bit about where this concept in the US came from. So I think one possible source of this project you can imagine is this paper that was published in 2015, actually just before the first detection, a gravitational wave detector with cosmological reach. So I've just included the kind of the top part of that paper down here. There was a study team assembled in 2018, kind of coalescing around this concept. And the concept was, as I mentioned, not just another LIGO upgrade, but this entirely new facility. So the idea is to think big in a couple of ways. This should be the ultimate facility, at least in the US, for ground-based gravitational wave detection. So something that should have a kind of long lifetime and allow for upgrades in terms of detector technology as we go forward. So the first tangible major step here was to produce a horizon study, which was just released in October 2021. So a bit about the Horizon study. So this was an NSF-funded study to inform the scientific community and funding agencies about the project, Cosmic Explorer, while providing a foundation for further development. So what that looks like in practice, there's many aspects covered in this study. A look at the kind of science that's enabled by Cosmic Explorer, this reference concept. So, how many detectors, what size, a little bit about the interferometer technology involved, and then some trade studies in terms of how to best use available resources to get the best science as well. And it does include also a cost estimate for what this project would eventually cost. So at this point, I'd really like to advertise, just take a look at this Horizon study. I think there's a lot of interesting discussion in there. And it would be, I'd also like to encourage you to endorse it, so you can endorse this study. And that, of course, helps to show community support, which is necessary in the long run. Okay, so a bit of an overview about the observatory itself. So what are we really considering here? You'll have seen on the title slide this kind of artist rendering of what a facility might look like. We're talking about an entirely new observatory on the ground, so not underground. Some of you might be familiar with Einstein Telescope, which plans to be built underground. Cosmic Explorer is not intended to be underground. And the reference concept right now is to have two L-shaped interferometers of 40-kilometer arm length for one and 20-kilometer for the other. So the idea behind making the sensitivity about 10 times better than advanced LIGO or A+, is relatively simple. It's just a matter of scaling up. So as we know, gravitational wave effect is a strain effect. The bigger the baseline, the bigger the signal that you are trying to measure. So if noise sources stay the same, you make the detector 10 times bigger, you get 10 times better strain sensitivity. It's a little more complicated than that in the details, but this is the basic idea. Just to scale up proven LIGO technology. So this would form, if all goes well, part of a global network, again, operating in tandem with the Einstein Telescope in Europe. Of course, there's major benefits to having global networks in terms of signal localization, source localization, and other confirmations of signals and parameter estimation. So the other thing that I wanted to mention, just to kind of highlight, is that we're not talking about, as I said, a single upgrade. We're talking about a new facility. So this should have room to grow in the future. So we have a baseline concept for how to reach this kind of baseline sensitivity. But the idea is to build the facility with future upgrades in mind, so that as technology progresses in the coming decades, we can take full advantage of that. Okay, so I'm going to get a little bit more into the interferometer concept. So as I mentioned already, most of the sensitivity enhancement we envisage, at least for the first implementation of Cosmic Explorer, just comes from the length. So we're talking about 40-kilometer or 20-kilometer arm lengths compared to the 4-kilometer of advanced LIGO. Having the pair of interferometers with different arm lengths actually helps to avoid the bandwidth limit of only having a 40-kilometer detector. For 40 kilometers, the free spectral range is, I think, 3.75 kilohertz. And so we have a little null, a little dip in the sensitivity at that frequency, and it's actually helpful then to have a second detector with a slightly different null. Keeping things simple is, I think, important at first, so we can reduce technical risk by just using proven A+ technology. So that's 1 micrometer laser, fused silica optics operating at room temperature. And we can still reach an extremely good science return with these proven technologies. On the other hand, there should be a parallel R&D effort towards future or alternative technologies. So for example, 2 micrometer silicon optics, cryogenic operation, with a view to future upgrades, or in case we encounter difficulties, unexpected difficulties with the baseline plan. So I'll run a little bit through the noise budget. So you can see the noise budget here on the right. If you with various kind of fundamental noise sources. And we could see, so the gray line there shows the total, the sum of all those noise sources. And across the band of interest, there's really two fundamentally limiting noise sources. So those are quantum noise, which is a major limiting noise source, of course, in advanced detectors, but also Newtonian noise, which is something we haven't yet tangled with too much in the advanced generation of detectors. So those are going to be the fundamental limits. Newtonian noise, just by the way, is the direct gravitational coupling of density fluctuations in the environment around the test masses to the test mass position. So you cannot fix this one by having improved suspensions. We need to do things like active cancellation or post-subtraction of Newtonian noise. So just a list here of the assumed technologies in this sensitivity curve that you see here on the right. So we're talking about 40-kilometer arm length for the plot you see there, 320 kilogram test masses. This helps actually a lot with the quantum noise. At the low frequency end, it's radiation pressure noise we're talking about. More massive mirrors are just harder to move by the radiation pressure force, so that helps. Much bigger and much bigger suspensions, so 4 meters long, 1,500 kilogram total mass suspensions for reducing seismic noise at low frequencies, 1.5 megawatt of light power in the arms. We assume 10 dB of frequency dependent squeezing, which actually on a tabletop experiment has just been demonstrated at the AEI for a Michelson. Balanced homodyne readout, like the plan for A+, and about between 10 and 20 dB of Newtonian noise suppression by this methods I mentioned earlier. At the low frequencies, I think it's important to note that fundamental noises are one thing, but when you get towards the low frequencies, there's a lot of technical noises associated with the various control loops that need to be engaged to keep the interferometer at its operating point. And there's going to need to be a lot of development in that direction too. Okay, so when you're considering a new facility, the site selection, of course, is a critical part of that. And that comes hand in hand with community engagement, actually, in the way we envisage it for Cosmic Explorer. So we'll consider many aspects, of course, environmental noise, the ability to acquire the necessary land, environmental impact, but also a big part of what we want to consider early on, and not as an afterthought, is engagement with local and indigenous communities. So getting this started early, so connecting these communities with Cosmic Explorer, we think in the long term is going to be crucial to the project's success. So this involves many of these aspects you see listed down here. Certainly obtaining local consent for the building. This is going to be a big facility, so it's going to have an impact on the local population. Building these relationships early on and getting people involved in a positive way as much as possible. Another aspect here is that the idea is to operate as an open data facility. So to get the data to the public who paid for it through their taxes early. Okay, so I'm going to move on now and talk a bit about the science objectives of Cosmic Explorer. So these are kind of illustrated in this this circle here, this sort of pie chart. We split it into 3 major science objectives, and I'm going to go through each one briefly. So the first one here is black holes and neutron stars throughout cosmic time. So this illustration on the right, I think is great for getting an idea of the cosmic scale of what we can achieve with these detectors. So on the left, you see these kind of horizons for neutron star in-spiral systems. So those yellow dots are neutron star in-spirals. And you see those horizons corresponding to the different detectors. So Cosmic Explorer is that pink horizon going all the way out to redshift of 10 for neutron stars, and even beyond for 30 plus 30 solar mass black hole binaries. And so what you can see here is actually, by the time you get out to that pink line for the black hole binaries and the green line for Einstein telescope as well, we're actually capturing signals from almost all the black hole binaries in that mass range in the entire observable universe, which is really quite a leap beyond what we're doing right now. So we'll have access to lots of exciting signals there, remnants from the first stars, population 3 stars, get ideas about the formation of supermassive black holes, different formation channels and galaxy formation, and just really conduct a survey of these stellar mass black hole populations. Moving on, the second major science theme is the dynamics of dense matter. And this, of course, mostly comes from the neutron star in-spiral signals. So here we see a quantum chromodynamical phase diagram. Excitingly, with detectors like this, we have access to a region of this phase diagram that's just not accessible in any other way. So we're talking here really about precise measurements of neutron star mergers and the post-merger phase. So with high signal-to-noise measurements of these events, we can really start to probe the dynamics of this dense matter and understand more about the neutron star equation of state and so on. So there's a lot of exciting science to be done by accessing these signals with high precision. And then third, we have the extreme gravity and fundamental physics. So this is really an extension of science that's been done already with advanced LIGO and advanced Virgo, but to the to another level of precision, essentially. So by having more precise, higher SNR measurements of black hole mergers, we can test the strongest gravity here, and even start to pick, possibly discount or maybe even prove theories for unusual compact objects like boson stars and so on. And this has implications also for modifications to general relativity or also dark matter and dark energy. So exciting.
Paul, how many more slides? We need some time for discussion.
Okay, I will try to flip through a little faster. So this slide just shows kind of the level of the precision that you could measure GW 150914 with for Cosmic Explorer. Gets an idea of the kind of regime change between the advanced and the next generation detectors. So I'd like to say a bit about synergies with LISA and Cosmic Explorer science. We're looking at black hole binaries in different mass ranges, of course. So LISA is looking at the heavier mass sources. So by combining both, we can really get a better picture of the evolution of black holes throughout time. Yeah, I think there's a lot to be gained by combining observations and data analysis between these. One aspect of synergy we will have heard about before is the idea that LISA sources evolve into the LIGO band. By the time LISA is operating, that should be, in essence, the next generation band. So that can be helpful for EM observations, of course, but also, if there's any tuning to be done of ground-based detectors. I think another thing that's worth considering is the same can work the other way around. So there's an interesting paper that I've just mentioned here, where you can actually use triggers from Cosmic Explorer and other next generation detectors to dig out sub-threshold events from the LISA data as well. So it's an interesting example of it working the other way around. Okay. Oh, should I?
Time is almost over.
Okay. I'll then finish with just the kind of, I'm going to skip this and just look at the kind of expected timeline going forward. So we're right here at the end of the Horizon study. The next stage will be trying to get a conceptual design together, so more detail for the facility and the interferometers. And then, as that progresses, more detailed designs, and eventually the idea is for construction to begin in the early 2030s, and then all going well, having observations actually coinciding quite well with the start of LISA observations. So I'll probably just leave it there for now then and take any questions.
Thank you. We have quite some questions. David Robertson asks, how do you plan to measure the Newtonian noise to do the subtraction or suppression?
Yeah, that's a good question. So that would be, I think the baseline there is essentially to have an array of seismometers around the test masses, and then to correlate those kind of environmental sensors and subtract from the gravitational wave data stream. But this is an active area of research right now.
Shweta asks, are there planned locations already? Canada be an option?
That is, well, let me answer the first part first. So there have been some sites which have been investigated, but I wouldn't say we have as far as a selected site already. It's too early for that right now. Would Canada be an option? I think that's more of a political question really than a science question. Not one I'm equipped to answer right now.
Asks, what is the main advantage of going to 2 micron?
Yeah, so going to 2 micron allows you to use silicon, crystalline silicon as the test mass material, which is opaque for 1 micron. And the advantage of silicon is that at cryogenic temperatures, we actually have a zero crossing in the thermal expansion coefficient, and that helps with reducing thermal noise.
Mm. And maybe I have also a question. I remember from earlier discussions that with such long arm lengths, there may be an issue with the 2 test masses not hanging parallel anymore because of the curvature of the Earth. Is that something you have to consider?
Yes, in a way. So actually, funnily enough, I do have a slide about this and bonus slides here. So this figure down at the bottom shows the issue you're talking about. So yeah, you're right that we have basically a vertical to longitudinal coupling due to the non-parallel G vector at the end stations. And so what that means, that coupling basically scales linearly with the length. And so for a 10 times longer detector, you have a 10 times stronger coupling. However, of course, the signal goes up by a factor of 10 as well. So you're kind of back where you started. So what this really leads to is a requirement for about a factor of 10 better vertical seismic suppression. And so part of this essentially leads to some impacts on the suspension design, primarily requiring vertical spring blades for the final stage suspension, which is not used in the advanced detectors.
Mm. Thank you. More questions? Okay, then let's take 13 minutes of break and start in 1/4 past on time, please.
Thank you.